Now for electrolysis 2, we're looking at the second part, that's electrolysis 2, and there's one more, 3. But for today, we're looking at 2. Now note that electrolysis is a process you need to understand for chemistry. Whether it is GC, O-level, CSEC, advanced university, it's a chemistry, note that. It's the second of 2 quizzes on the subject, but what exactly electrolysis and what is this and how it was discovered? How was it discovered? Now, first and foremost, electrolysis is a method of using a direct electric current, like I would have outlined to you last week, to cause a chemical reaction. So if there's not a direct current, then there's no chemical reaction occurring. To cause a chemical reaction, remember that, chemical reaction. Now, it was discovered by accident. Now, they're saying, remember, if you look back at people such as, we want to go way back to Edison, who discovered a light bulb. We probably would want to look at this other guy, Kepler, and these people that would have played with electricity. But it was discovered by mistake, so to speak, because they weren't looking really for that. They were looking for electricity, basically. Anyhow, let's read on. Electrolysis was discovered by accident in 1800 when the scientists William Nicholson and surgeon Anthony Carlese attempted to reproduce the experiment in which Italian scientist Alessandro Volta. Now, in physics, you will look at it, you probably, anybody did the voltaic cell in physics? Anybody looked at the voltaic cell in physics as yet?
No, sir. No, sir.
Okay, good. Oh, right, nice. So if you would have done so, then you'll appreciate that electricity basically deals with voltaic cells. Now, the most important thing is having an understanding of how it functions. That's the most important thing. Anyhow, let's go back. It was discovered by accident in 1800 when the scientists William Nicholson and surgeon Anthony Carlese attempted to reproduce the experiment in which Italian scientist Alessandro Volta created the world's first battery. Instead of using frog legs, that's frog's legs, because you can use that to test current as well, to test whether electricity was produced. They were using a device developed by Nicholson similar to the gold leaf electroscope. Now, if you had dealings with the gold leaf electroscope, you will understand how that functions. That's in physics. But it's very important to know how that operates. To get a better contact between the wires from their battery and the measuring devices, they use a drop of water. When they noticed that a gas was bubbling off from this water, they investigated further and were astonished to find that when they passed the electric current from their battery through river water, there was a reaction. A gas bubbled off from both wires they had dipped into their sample. That was the first time electrolysis was seen. Now, you would recall last week when we were dealing with this scenario, and I said to you, picture how you're setting up. I went through the process with you, how to set up an electrolytic cell or vessel. So when they passed that into the water, the same thing they did. They were fascinated to notice gas bubbling off. And so right away they assumed, right, that this whole process was electrolysis. Very interesting, very interesting. Now let's move on to the second paragraph. A few years later, in 1807, potassium was discovered by Sir Humphrey Davy. And this is important. These notes are important. So I would like you, in your free time, to underline the most salient points when potassium was discovered and so forth. I might have quizzes on these or so on. Sir Humphrey Davy, whilst using electrolysis on molten potassium hydroxide. Later in the same year, he discovered sodium using the same method. So because sodium and potassium is in the same group, you can use the same method. The following year, he discovered barium, calcium, boron, strontium, and magnesium too. So unlike the two, the following years, the years that follow, he would have discovered these. But it was the assistant of Davy who worked out the laws of electrolysis. So they had to work out the laws of electrolysis. Michael Faraday. You must have heard of him because I think you would have done, well, it's now you're doing electrolysis, sorry. Well, okay, in physics to some extent. But really, let's look at the chemistry. These laws enable scientists to predict and plan how much of each substance can be produced from electrolysis. He also introduced the terms used in electrolysis that you are familiar with, such as anode, cathode, electrode, and ion, which you would have covered, although they were actually invented by the master of Trinity College. Now, these were actually, they became more, well, they're not really invented, but actually they became more pronounced, I would say, right? In university. Remember when these people would have tested these things, some of them would have been really not in a university as such, because yes, they had universities, but not all scientists would have been at a university to carry out tests or experiments on these things, right? Some of them would have done it in the backyard, maybe in a kind of an area where that can be considered good, so to speak, conducive to working, right? Third paragraph. Once electricity generating equipment had improved and electrolysis was better understood, the commercial value of the process was realized and it was taken up by industry. So hence, after things became better and maybe persons, became more interested in its production, they took it up in commercial quantities, because remember now it can be sold. People get more interested and want to buy in bulks and all these things, right? To market, to use and all these things. So commercial quantities would make things better. The process was realized and it was taken up by industry. So industries now took over and started to manufacture these things. The first large-scale electrolytic cell were developed in the 1880s for the electrolysis of brine, which we spoke about, which gave birth to the chlor-alkali industry. That's an industry. It's actually chlorine alkali industry. Also, during the same decades, the Hall-Root process for the extraction of aluminum was developed, which transformed aluminum from a rarely seen and extremely expensive metal into the cheap and widely used metal of today. So, actually, because industries opened out, they were able to subsidize costs because they are manufacturing on a larger scale. So everyone can get it. So costs will reduce significantly. Remember, I know some of you, well, I don't know, I know you're in science, but I know to some extent you may have family members or so on that maybe they're dealing with economics. And so we know if a shop in a community has only, let's say, flour or oil, they will sell it at an extravagant price. But the minute other shops within that community open up, that price will significantly fall. It will drop to compensate for everyone to buy. So it's something like that. In the inception, you had one place having all of these things. So there were a tremendous cost people had to pay. But because industries open up, and maybe local stakeholders came in and so on, the cost was reduced significantly to facilitate maybe purchasing and so on by others. So that's how it became cheap. Good. Now, right, so the Hall-Root process for the extraction of aluminum was developed, which transformed aluminum from a rarely seen and extremely expensive metal into the cheap and widely used metal today. There were no health and safety at work regulations at the time. In other words, the occupation safety and health that you have today, you did not have that before, because a lot of people weren't cognizant of the harm that these things would have caused then. You would have read about Marie Curie. She dealt with a lot of radiation, and as a result of that, she would have died from radiation, but at that time she did not know the devastating effects that radioactive materials would have caused. So she suffered the consequences. You're gone. Okay, miss. So all these things are of concern. You need, and that is why you have a lot of safety practice today. You have a lot of occupation safety and health that are reinforced in organizations so as to safeguard workers and protect certain, protect the overall health, so to speak. You find that if you go into an industry, they ask you to wear your PPE. That's your personal protective equipment. You should always have, if you're going into, let's say, a chemical plant or an electrical plant, or where if you go to a mechanical plant, they ask you to wear a hard cap. You have to wear gloves. You have to wear steel tip boots, protective gear, right? All these things are considered extremely important because you're already risking yourself to be in an industry that has a lot of machinery, maybe a chemical plant or mechanical plant or electrical plant, so you don't want to suffer the consequences. So now they have implemented all of these things, and you call them occupation safety and health hazards, so that you can have their guidelines to follow. You can look at them and see and protect yourselves, right, from any imminent danger. But back then, in the 1800s, the 1700s, early 1900s, you didn't have these things. And so when bridges and construction work was going on in various parts of the world, various countries of the world, like for instance, the building of I don't know if you know this, but the Brooklyn Bridge, right? The Brooklyn Bridge was actually built in 1895, and a lot of people died there. I think several people would have met their demise because obviously they didn't put the necessary precautions in place. And so many organizations around the world would have lost people because of lack of the knowledge that they should have had at that time to wear protective wears and these things, but they did not do that. All right? Maybe they thought of it, or maybe they didn't have the equipment at that time, or maybe they didn't have the collateral, maybe they didn't have the money, right? Things like that. So you always have to be cognizant of what you do in life as a scientist. We put ourselves in harm's way. We might underestimate a chemical reaction in the lab, and so we go make a mistake, and that's it. In no time at all, you might be dissolved, right? You might be blown up. So you have to know what you're doing. And as scientists, we always go about with trials and errors, right? To look at the confidence interval is something that you do in your latest in your latter studies. Errors of margin, right? And so if something goes up by 0.1 degree, it can be devastating. If it comes down by 0.1 degree, it can be devastating. And that's why they call something called equilibrium, right? Which you will learn in fifth and sixth form. So pay attention to these things because these things are very important in life, right? Good. Now, so for this afternoon, it was a quick note there. I hope you will have this because I have it here, so you see. But I want you to look at this quiz now. So I will pass on the quiz to you, so you can begin your quiz. You all hear me?
Yes, sir.
Yes,
Nice.
sir.
So nice. All right. So go ahead and do your quiz. Remember, if you get knocked off, you can join back right away, right? Immediately, because I will sign up back again. I will not sign up. I will connect back again. All right. I will reconnect, so to speak. So go ahead and start the quiz, Sumi. Electrolysis, like I would have suggested to you. But I want to pick the correct combination of components for the electrolytic cell. So they're saying here, you're going to pick the correct combination of components for the electrolytic cell. Take your time, pick the correct answer. I'm trying to get a bottom one to show. Look at the options that you have very carefully. You got the cathode for the first one. You have the impure copper, the anode pure copper. What is left in the as the electrolyte? Copper sulfate. You have cathode, the second one, pure copper. Anode impure copper. What is left? Copper sulfate and electrolyte. Third, pure copper. Pure copper. Electrolyte is copper sulfate. And lastly, impure copper, pure copper. What is left? Water. Can I move up?
Yes, sir.
So choose the correct half equations for the electrolysis of brine. Half equations are basically, when you have the equation, you try to cross off all the spectator ions. Those are the ions that take part in the reaction. So once you take those off, you're left with the others. So if you're looking to see what will be formed at the cathode, remember electrolysis of brine. So right away, we know brine is sodium chloride. Therefore, what will happen at the cathode? What will happen at your anode? Look to see where hydrogen is in preference to the sodium. And you should be okay there. You'll also see as you work along, you'll also be able to know if something is balanced by simply looking at the equations. And if you check the ions, the amount of atoms you have to balance, right? So look at them carefully. You must notice something about them. Okay, moving up. Again, I want you to pick the half equation for electrolysis of copper sulfate. This time you're using copper electrodes. Copper electrodes. Now, if you're using copper electrodes, then the copper, as you can see, is taking place in the reaction. Nothing else, just copper. So you have copper at the cathode and copper at the anode. See what's happening there? You get copper at the cathode and copper at the anode, but which is the correct one? Which is the correct equation there? Or equations, rather. Let me give you a hint again. Remember when the copper ions get to the cathode, they become atoms. And then you're going to look at the order of the reaction in terms of how the arrows run. All right. Now, I'm moving up. Aluminium.
Sir, can you go back to the number 4?
Oh, number 4. Ah, that sounds like I know who. That's O'Brien?
Yes, sir.
Anyhow, back to work. But I didn't hear it from you, so I wanted to know what's happening. And like I said before, for those persons who might be encountering some amount of difficulties using a platform, I will presume that rather assume and more or less presume that you would acquire these notes from your colleagues. It's important that you get them, because remember, the more questions you get, rather multiple choice and all these things, you're able to create a test bank, like how CXC has a test bank, and then you can correlate the questions with those of CSEC to get to know how to answer others. So what we're doing here essentially is creating a test bank, so to speak. All right, I'm moving up. Aluminium ore, that's the bauxite, must be dissolved in molten cryolite before it can be electrolyzed. For those of you who don't know, molten cryolite formula is Na3, as in capital N, common A, you know, sodium, the symbol, a little 3. ALF, that's capital letters, capital A, L, that's aluminum, and F, that's capital as well, and a 6. So it's Na3ALF6, molten cryolite. You must dissolve it in molten cryolite. That allows it to be electrolyzed easily. Now, which would be the answer there?